of a bullet passing through apple. So everything was going on in dark. He was using flashes of light. 1 flash, 2 flash, 3 flash, 4 flash, like this. Okay, just like this. You can use it like this. Okay, but it has to be very fast to capture that event. I said that duration of this flash, how long this light would be, that has to be determined based on what kind of event I'm going to capture. If event is nanosecond, duration of the flash would be less than nanosecond. Less than nanosecond, what we have? Less than nanosecond? Picosecond. Very nice. Less than nanosecond, I have picosecond. What is picosecond? 10 to the power 12 second. Okay. Very nice. If it is going on in picosecond, what kind of flash of light I need? What is that? What is that? Huh? femtosecond, right? Okay. Very good. Femtoseconds. 10 to the power minus 15 seconds. Very nice. 15 seconds. If it is going on faster than femtosecond, what you need? A duration of the flash. You have Google. Use your smartphone. Find out. Less than femtosecond, what you have. Find that out quickly. Femtosecond. Is going to be attosecond 10 to the power minus 18 seconds. Okay. So one important concept we have clarified already. Rest of the discussion is just useless. Shall we go ahead or stop here? We'll stop. We'll not stop here. We'll go ahead. Okay. See, this is the image for the first time which was captured with the help of stroboscopic photography, and this came to the news. Okay. Everybody was happy, and everybody looked at the news except for one scientist, Norris. He was working in UK, and he didn't go through the newspaper. He was just sitting in the lab and thinking how to solve one problem. And the sweeper came to the lab. Sweeper came and he was asking what happened in UK, US. Their culture is they call by their name. Okay. Here we do it in a different way. So the sweeper asked, "What happened, Nourish? I mean, why you are upset?" Nourish told that I cannot solve this problem. And what was that problem? He was trying to monitor a chemical reaction. Any chemical reaction. Okay. We all know what does it mean by chemical reaction, right? Okay. He was unable to monitor a chemical reaction. And the sweeper said, "Why? You use my stroboscopic photography. I mean, I have seen this is the big news right now. You go ahead." So he asked, "What is the time scale of your chemical reaction?" He said that it's some kind of, at that time, it was microsecond. So, or some kind of millisecond. So he said, the sweeper said that, "Oh, then you use some kind of microsecond flash of light. You'll be able to do that. Go ahead, do it." He did that, and he got Nobel Prize for that. Okay, so this is really a big history. So this is first time. Okay. Okay, so this is here. I'm going to present this idea. You see, whatever I have told, something is going on in the dark. And what is going on in the dark? This dial is rotating. And with the help of my eye, I'll see a blur image. I'll not be able to recognize each event, how the dial is rotating. Okay, Yeah, exact position. Yeah, I'll not be able to locate it. But if things are going on in dark and I use a flash of light, and I know duration of the flash is going to be shorter than the period of the event, clear, I'll be able to capture each frame, and I see movie, right? That's the way movie will be made. I don't need a film. I just capture it at different time. Now we'll go back. This is a real life problem. We'll go back to the problem of the scientific problem. The scientific problem is that I want to capture a chemical, let's say, in any matter, let's say, Any matter. What you have? What are the constituents of matter? Huh? Atoms. Very nice. In atoms, what you have? Electrons and nucleus. Okay, I'll not go to protons and all this. They are too small. Okay, we'll forget. Any system you consider, any matter, I have nucleus, I have electron. So the first question, if I want to know how molecules are doing something in this room, there are a lot of chemistry going on here. Okay, and if I want to know all these chemistries in real time, the way we are capturing, okay, capturing image. If I want to do that, then I have to know what is the time scale of those events, molecular events. And molecular events, what does it mean? It means that what is the time scale of nuclear motion, right? What is the time scale of electronic motion? These are the things I have to clarify first, because based on that information, I'm going to now find out what kind of camera and what kind of duration of the flash I need. Okay, camera is a slow camera. I cannot do anything. Camera is going to be very slow. Oh, I'll be standing here only. Okay. So what we will do, we'll look at the vibration. Fine? We'll look at the vibration. And what does it mean by vibration? We breathe every day, right? Similarly, molecules are vibrating all the time. Okay? It's stretching, compressing. Two nuclei are vibrating. Okay? It's like vibrating. Yeah. See, this kind of, whenever I make this sound was heavily used in old Hindi movies, and somebody is, let's say, dying. Okay? So and that's a breathing mode. We call it breathing mode. A molecule is vibrating like this. Okay? So all we need to find out is that what is the time scale of that breathing mode. Let's say a molecule is dissociating. A dissociation of a molecule, how do you represent? Molecule is vibrating like this, but I can stretch these bonds to the limit of dissociation so that it don't come back anymore. It just go far apart, right? So all I need to know is that what is the time scale of this vibration, going from this configuration to this configuration, coming back to this configuration. One period of vibration. That I can find out. Do you know IR spectroscopy? Yes. IR spectroscopy you have heard. You know stretching frequencies, where they come? Give me one example. Stretching frequency. Any example? C double bond? You said something, double bond of... Okay, C double bond O. Where is the stretching frequency? Very nice. 2000 wave number. What is the unit? No. 2000 wave number. Okay? Yeah, centimeter inverse. Yeah. This is written here. 2000 wave number. Wave number is this one. Nu bar. I can multiply by C and I can get nu. Right? And nu can be converted to period. And what is the period I get? 16 femtosecond. You see? Now the time scale is coming up. Femtosecond is going to be the time scale of nuclear motion. And if I need to capture that, what I need, let's say the time scale of this vibration is going to be, let's say 200 femtosecond. Then what I need, what kind of duration of the flash I need? Okay, don't go attosecond. I can still go with 1 femtosecond. Is it fine? It has to be shorter than that. Am I right? Okay. So femtosecond, we'll keep it in mind. Femtosecond is going to be the time scale of nuclear motion. Okay. I have electrons also. Let's look at electron. If we look at electrons, we'll go back to our 12th standard. In 12th standard, we know Bohr atomic model. Okay. In Bohr atomic model, there are two forces in equilibrium. Two forces are equal. What are those forces? Centrifugal force and no. Centrifugal force is fine. Acting which way? Centrifugal force. Electron is rotating, is orbiting. Okay? So centrifugal force is acting towards nuclei is what kind of force is acting? No. Think about it. I have positively charged electron. I have a electrostatic, right? So this way electrostatic force, this way centrifugal force, they are equal. If you make them equal, you get velocity, right? From velocity, you know what kind of path length it will cover when it will make full rotation. Okay, wait a minute. Yeah. Somehow I'm not managing this. Okay, so when this will rotate, make a full one orbit, I know what kind of path length it will go, right? R is the Bohr radius, so I'll be able to get this whole path length. How long does it take to make this whole round? If you calculate, it will find out 150 attosecond. So electronic motion, the intrinsic time scale of electronic motion is going to be attosecond. Electron and nucleus, these are two different, they have entirely different masses. Do you know obesity? Huh? Do you have a friend who is obese? Very, very fat friend. Do you have no fat friend? Huh? Do you have relatively fat friend? You have? Okay. Try to push him. You'll see no effect on him. He will be standing like this. It's just like nucleus. 10 to the power 3 times higher mass. Okay, it's a big change in the mass. And a very thin, frail guy. Do you have any friend? Huh? Push him. Okay, push him. Yeah, push him. You will see, the moment you push him, okay, he will fly. He will go away. So that's the difference between an electron and nucleus. And because of their mass, the time scales are different. They are different. The time scale of the motion of an electron is very, very fast. What is the time scale of that motion? Attosecond. What is the time scale of nuclear motion? Femtosecond. Very nice. We'll keep it in mind because I need to know the time scale of the event to figure out what kind of pulse duration I need. Okay, I'll go back how to create those pulses. Before I do that, let's go over quickly what kind of contributions scientists already have made, and that can be very encouraging to know. In physics, 1964, there is a Nobel Prize given to these people for developing sophisticated flash of light. What is that sophisticated flash of light? I have to tell you. I have to tell you, do not think that flash of light like this can be synthesized like this. You cannot synthesize it of that duration. Why? We'll talk about it. Okay? So they actually created this laser. Laser, have you heard laser? This is also a laser. Okay. This is called sophisticated flash of light. We'll create that sophisticated flash of light. What does it mean? I'll come back. But they actually synthesized it. Okay. Then in chemistry, I told you now that sweeper example. This is the person. Where is Norris Port? Edgarden, not Edgarden. This is the guy. Okay, this guy. He was very upset. Yeah, he looks upset, right? If you look at him, he looks upset. Very, very upset. But he actually got that idea from the sweeper, and sweeper told him that there is a news. You go through this stroboscopic photography. Why did you use that one for your chemical problem? Okay, he used that, and he got that Nobel Prize. Okay, with others. So this was for their contribution to study extremely fast chemical reaction. In 1960s, extremely fast, it means microsecond. But today it is fast. What is fast? Attosecond. Okay. Okay. Then 1981, again, laser spectroscopists in physics, they were given Nobel Prize for their contribution. Okay. Again, spectroscopy. What does it mean in spectroscopy? I told you it is the light matter interaction. So they have studied light matter interaction spectroscopy with the help of laser. That is the sophisticated flash of light. Okay. 1999, again chemistry, they have got Nobel Prize. He actually studied chemical reaction in femtosecond. Improved. See, Norris studied in microsecond. He studied in femtosecond. Okay. And in 2018, they got Nobel Prize because they were able to generate very short pulse. I haven't discussed how to generate a short flash of light. Very short flash of light. A flash of light which will exist for, let's say, femtosecond time. Femtosecond, can you imagine femtosecond? What does it mean? It's going to be, you have to divide 1 by 10 to the power 15. Then that little duration of flash of light. So what they did, they got Nobel Prize in physics because they were able to create very high intense flash of light of femtosecond duration. Very intense. And the technique is called charred pulse amplification. We'll talk about it. If the time permits, we'll talk about it. What does it mean by that? Okay. So this was the kind of an introduction we had to tell you what technique I need in order to solve this problem. Okay. Now we'll go back to the problem of how to create such pulse. I told you, I have given a hint that this technique, what I'm doing right now, flash of light. I'm creating flash of light. This technique is not enough to create this duration of this flash. Cannot be made femtosecond or even picosecond. Question is why? You have to give me the answer because I have given you the clue already. I want to make it like this. My hand is very slow. Okay? An old man's hand will be even slower than my hand. Okay, so I cannot depend on hand. Manually, right? I cannot do it manually. I can do it electronically. If I am doing it with electronically, what would be the shortest possible duration I can have? Electronics response time, microsecond, better than microsecond, nanosecond. Very good. You are coming up with this plan. See, if I want to convert this manual way of doing flash of light to the electronic way of doing flash of light, then the best shortest pulse duration I can create is going to be nanosecond. I'm stuck there. But in order to capture molecular event where nuclei will move, electrons are moving, I need femtosecond or attosecond time scale. How to achieve it? Again, I'm falling into the same dark ending, right? So the way you can generate it, not by electronics or anything, the way you are going to generate it with the help of optical interference. And everybody has studied this optical interference. You know bit, how to create bit? How do you create bit? In sound wave we have studied bit. How do you create bit? Remember, two waves, two plane waves, sine waves, propagating along same direction, having slightly different frequency, right? They will create bits. What does it mean by bits? Okay, bits are nothing but localization of that energy in time, right? So during that time, you are localizing the energy. Now imagine I have all these. This different color means different frequency, slightly different frequency. And look at this; they are all interfering. Somehow, at this point, we will think that there is a source. Just like this source having all frequency, right? In this room, this light source having all frequency, what I need. White light is nothing but many frequencies. Okay, so I have all these frequencies. Somehow, let's say, but this is different and this is different. This is not pulsing anymore. There is a reason for it. We'll find that out. Somehow, you have been able to manage to bring everybody in phase. This is the regime. You see, you have somehow managed to bring all frequency components at the same time at this point. Because they differ by frequencies or wavelength, they will be destructively interfering some other place, here constructively interfering, and here again destructively interfering. So what will happen in the end, light energy will be localized mostly here, nothing. Then again after a certain time, again there will be constructive interference, right? Constructive interference, destructive interference, constructive interference. So the regime where mostly constructive interference are going on, there you are localizing the energy. Okay, and that's the way you have to create the flash of light. You cannot use any electronic device. Okay, so what does it mean by plane wave? What is plane wave? Okay, so here I have shown one more time. This will be a better demonstration. You see, in this regime, in this time, it's constructively interfering because they are in phase. What is phase, by the way? I'm saying phase, right? What is phase?
State of vibration.
Huh?
State of vibration.
Okay, state of vibration. But can we just get a little bit better physical meaning? What does it mean by phase? Let's say these two plane waves are propagating wave. If I had one wave, I could have taken a reference of this wall and said that this much progress it has made. But if I have two waves, relatively they are propagating, right? So there is a physical quantity which is expressing their relative motion, right? Let's say relative position of this tip, and that is the phase. The phase is a physical quantity which is describing the relative motion of these two propagating waves. So somehow you have to bring them in phase so that at this point of time they will be interfering constructively, and at this point they will be destructively interfering. Again, constructive, destructive. Okay, and as a result, what you get is localization of energy here, again localization of energy here, localization of energy here. I cannot create one flash of light. A flash of light will be created in a period, always, because these waves are continuously propagating. It will be continuously interfering. So from the source, there will be a burst of energy, one burst, two burst, second burst, third burst, fourth burst, like this way, this burst of electromagnetic energy will come. And one more thing we have to clarify here is that if I had two such if I have, let's say, two frequency components, then what will happen? Their interfering regime would be very, very long. And that's why very long pulse I'll be able to create. If I need to create a very short pulse, I need many frequency components. And time and frequency, they are correlated. How they are correlated? They are correlated, we know uncertainty principle, Heisenberg uncertainty principle, you know? What is that Heisenberg uncertainty principle? Huh?
Additional momentum simultaneously
Cannot be measured with the same precision. Okay? It can be measured. You can go and measure. But question is, what would be the precision of that measurement? If you try to measure the time very precisely, you have lost many information about the energy. Similarly, this is also true here, and I'll show you this product. Okay, it looks familiar, looks similar to time energy uncertainty. What does it mean? It means that, let's say, I want to create very short duration of the pulse. Delta t is the duration of that flash of light. I want to create that. If I want to create that, then my source should have very, very large delta mu because it's inversely proportional. Which means that a source which will be giving you many, many frequency components, they all have to interfere together to give you a very short pulse. So, for femtosecond and this delta mu, technically it is called bandwidth. Bandwidth, what does it mean? The spectral width. So, I'll draw this way. I'll draw it like this way. I have a source. I have a source. I have a source. This source, what kind of source will go over very soon? I have a source, and characteristics of this source is that it has a bandwidth like this. Bandwidth, what does it mean? In omega or nu, let's say. This is the spectrum. What kind of spectrum I have? Let's say this source. If I take this source has a number of frequency components. So if I take a spectrometer, I can bring a spectrometer. What is spectrometer, by the way? Measure spectrum, but what do you have? How do you measure spectrum? How do you measure spectrum? In terms of wavelength, but what would be the device which you need? Spectrometer. In spectrometer, what do you have? In spectrometer, what you should have? Just think about it. What I need to do? I want to find out what are the frequency components I have. So, I have to disperse the wavelength. Can you tell me one dispersive material? Prism. Very nice. Grating. Right? I can have a grating, I disperse it, and I have a little camera, and I change the grating. I'll be able to get to know at what wavelength, what is the intensity I have. Right? Yeah, and then if I plot it, let's assume that I have this kind of plot. Always any source will have this kind of distribution. Let's say Gaussian distribution or Lorentzian distribution. Okay? So this is my spectrum. Spectrum gives an idea how many frequency components I have. I have 1, 2, 3, 4, 5, 6, 7, 8, all. Mostly infinite, let's say. Right? I cannot tell you the spacing between it. I have so many frequency components. Let's say I have Avogadro number, 10 to the power 23. Let's say I have 10 to the power 23 numbers of frequency components I have. And they are all interfering. Due to this interference, what I'll have, in the end, I'll have pulses coming out. And duration of this pulse is going to be, let's say, femtosecond. I want to create attosecond pulse. What I need then? What I need? No, what I need? I need a source which will give me more frequency components. Right? Because delta t, that is the duration of the pulse, is inversely proportional to delta mu. I need very, very large delta mu. Delta mu is this width, delta mu. This width is delta mu. I need very, very large delta mu to get very short pulse. very large. Bandwidth, I need very large bandwidth. Okay? So this is something which you should remember. And when you are remembering, there are many issues now. Issues is that when you are dealing with a pulse, optical pulse, it's more like at home, we have mother and father, right? Both of them playing an important role. You cannot imagine one without other, right? If you omit one of them, then the stability of that family will be gone, right? But at a time, let's say you came home and you are seeing your mother is working. That doesn't mean that your father is not working. Your father is also working, but you haven't seen it. So it's something like that. Mentally, it's very difficult. When you are thinking about the pulse in time domain, there are two domains now, just like mother and father. There are two domains in pulse. One is time domain, another one is frequency domain. When you are thinking about time domain, you are thinking about interference. Okay, interference, you get the pulse, everything is okay, but that pulse will be propagating through the medium, right? Remember, it is not the time duration which is propagating, a temporally localized electromagnetic energy which is propagating. At the same time, this whole bandwidth is propagating in the frequency domain. So to visualize both of them is very difficult. And Wigner, have you heard about this scientist, Wigner? Wigner was a scientist who was able to see both domains simultaneously. It means that you entered the home and suddenly you found that your mother is working. Immediately, your brain is calculating what your father is doing immediately. You are not seeing your father, but you are calculating immediately. Okay, Fourier did the same thing. Fourier, have you heard about Fourier? Fourier transform, Fourier series, Fourier transform. Fourier did the same thing. Okay, Fourier was able to see both domains simultaneously. But for us, suddenly, if I tell you a localized energy, which is due to the interference, I told you how interference is going on. That is the time axis. X-axis is the time axis there. So time axis means I'll call it a temporarily localized electromagnetic energy propagating through the medium. But at the same time, you have to remember this localization is due to interference of all these frequency components. So you are actually not alone. Those many frequency components simultaneously propagating through the medium. And we know what does it mean by dispersion effect. What is dispersion?
Separating Gaussian colors.
Yeah. So dispersion, what does it mean by dispersion? Dispersion is it is the variation of the refractive index with respect to color. Okay? Variation of refractive index with respect to color. It means that I have two colors, let's say, red, blue. These two colors I have. If these two colors are propagating through this medium, through this room, what will happen due to dispersion? What is dispersion? Dispersion, I will show you the dispersion. What does it mean? Refractive index will change with respect to frequency. This is the normal dispersion we see. This is refractive index, this is nu. Right? That's dispersion. Refractive index is changing. What is refractive index? What is refractive index?
Ratio of velocity.
Yeah, in terms of velocity, what is refractive index? Refractive index has different meaning, right? You can think about refraction angle with respect to refraction angle. That's Snell's law. Forget about those geometrical things. Talk about velocity. Tell me what is refractive index? N equals refractive index, velocity of light in vacuum divided by velocity of light in medium. Right? That's your refractive index, index of refraction. Now just imagine If in depends on frequency color, then velocity of that frequency component will depend on color. So I have two colors. I have red color light, pure red color light, only one frequency, imagine it, and pure blue color light. Both are propagating in vacuum. This is vacuum, let's say, propagating in vacuum. What would be the velocity for both of them? What would be the velocity for both of them? Same, but what? Velocity of light in vacuum. So they will be propagating like this. Newly found girlfriend, boyfriend together. Okay? But in the medium, think about the medium. Velocity is going to change now. Whose velocity will be faster than blue? Red would be faster than blue? Huh? Red would be faster than blue? Tell me, confirm me. Is it true? Red is here, lower frequency. Blue is higher frequency. Right? Red is faster than blue. Okay, very good. Just like after getting married, after spending 20 years, husband is like this. Okay? It's just a dispersion. Nothing wrong in it. It's just dispersion in the medium. Okay. Now you think about it. There's a problem. This is going to affect my pulse. My pulse is nothing. I said that pulse has two domains, two different domains. One domain, time domain. If you stand on time domain, you are blind to the frequency domain. You cannot imagine frequency domain. But many things is going on frequency domain, and mostly it's a dispersion effect. If you stand on frequency domain, nothing you are seeing in time domain. What is going on in the pulse duration? You don't know. So all you need to do when you are thinking about a pulse or sophisticated flash of light, you have to stand on both. See what is going on here, what is going on here. Okay. That's the way you have to go. And what kind of mathematical tool which will enable you to go from one domain to another domain? It is called Fourier transform. That's a very sophisticated, very simple idea which can help you transform from one domain to another domain. Let's say you are in time domain and you have a suspicion, you suspect that something is going wrong in the frequency domain. Let's go to the frequency domain. What you do? Fourier transform. Okay, you are in the frequency domain. Then you want to go back to the time domain. Inverse Fourier transform. Come back. Time domain. And always you do that. Otherwise, you have lost half of the information. Okay? Now, what is the problem? What kind of dispersion problem I can have in a pulse? That's the question, right? I said that in medium, red is propagating faster than the blue. What kind of effect you can see? The effect is that, see, in vacuum, you have created, let's say in this room, I have created a very short pulse. And very short pulse means it has a huge bandwidth. All those frequency components were in phase. In phase means standing together. Newly found girlfriend, boyfriend, standing together. They are going together in the vacuum.
It's relative motion zero.
Yeah, relatively there is zero. But then in the medium, red will be going faster. And the moment I have shown you those interference pattern, the moment you are, so what is going on when they were together, you had a very short pulse. Now they are not together, they are moving like this. You are stretching the pulse. Getting the point? You are actually stretching the pulse. So the pulse which you created, a very short pulse, when it's propagating through the medium, is getting stretched. It is actually becoming broader, a broad pulse, which you don't want. You have to bring it back. So there are a lot of mechanisms which you need to follow to construct such a laser system. Okay, we'll go for the construction of the laser system. In a conference, somebody was presenting his work. Okay, he was very excited what he was presenting. See, blah, 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 blah. Many things he is presenting. And then he was almost at the end of the talk, and he wanted to present more. Okay, he had a lot of energy at that time. He wanted to present more, and he asked the audience, tell me, how much time I have? Tell me, how much time I have? I have too many things to present. And nobody was giving answer because he was an eminent speaker. He was a very big shot. I mean, and everybody was silent. Then from the backside, from the rear benches, somebody stood up and then said that you can speak as much as you want, sir, but we are leaving in 5 minutes. Okay, so that might happen if we don't maintain the time. Okay, so we have 1 hour. Oh, we have a lot of time. Okay. So what we'll do first is that clearly we have got an idea that time and frequency, these two domains are highly correlated domains. We cannot forget one and look at other. They are going to affect each other. But if you stand in a single domain, you'll be able to never get an idea of how this effect is going to contribute. The pulse which you thought that I have a short pulse is propagating through the medium, it will be stretched, a broad pulse. And you don't want broad pulse because your event is fast. Your event is very, very fast. You have to capture that event with the help of stroboscopic photography. Okay. Now question is, how do I synthesize? How do I create those pulses? Okay. Okay. So how do I create the pulse? Beer-Lambert's law. Have you heard Beer-Lambert law? Huh? Photochemistry, yeah, photochemistry. Beer-Lambert's law. What is Beer-Lambert's law? What is Beer-Lambert's law? Say something. Beer-Lambert's law suggests that intensity as
monochromatic source of light passes through the homogeneous solution.
Okay.
Intensity increases over time.
due to intensity is decreasing due to absorption. Medium will absorb. That's why intensity will decrease. I have a liquid column, let's say. I use one liquid column and I place this wax lamp. Okay, I just place it like this. So then in liquid column is going through it, and how the intensity will drop down? It will drop down linearly or exponentially. It will be dropping down exponentially. Exponentially it will drop down the intensity of that beam, and that's exactly what I am showing here. Intensity when it's going through the medium, the transmitted intensity is going down linear exponentially as a function of length. That's called Beer-Lambert's law. Okay. In laser system, you see exactly opposite. What does it mean? It means that when I use a very weak source, I use it, more it propagates through the medium, it will be intensified. It's just an opposite word. Okay? Have you tried to visualize yourself from this side? Have you tried to visualize that? You'll see that the whole world has changed. There are two species in biology. They try to visualize the world like this way. You have to tell me the names. There are two species. I know at least there are many. Bats. Very nice. And at home we have spider. Both of them are staying like this. Okay, upside down. So similarly, this one is just upside down. Generally, what will happen? When the beam will propagate through the medium, it will absorb and intensity will drop down exponentially. But in laser medium, it's just intensify. It will intensify. Now, question is, you You cannot intensify suddenly. What is the mechanism? How can you intensify? Absorb. It can decrease. That I understand. Why? Absorption. Material is absorbing. Material is taking energy from that electromagnetic source. Is taking energy. But intensify means material is giving energy. How can you give energy? Okay? And that's all about laser. See, the name laser is the light amplification. That's intensify. Okay? Yes. By stimulated emission of radiation. So how can you intensify? By stimulated emission. Okay. What is stimulated emission? In 1913, probably, Einstein proposed three mechanisms how light can interact with matter. There are three mechanisms. One mechanism we have already said, that is the absorption. Absorption, when molecules will be excited to the excited state, this light energy will be absorbed and molecules will be excited to the excited state. That is absorption. So light energy is converted to the molecular energy. Molecule is excited. Okay. Then there is a process called spontaneous emission. What is spontaneous emission? Yeah? Lower energy level? Energy level. It emits the energy as a radiation. Okay. That's called spontaneous emission. Now, interesting thing is that if I have 100 molecules, I'm excited. And then trying to find out when they are de-exciting. Because if they don't de-excite, I'll not get energy back. Huh? What is that?
Say it's on a state of 10 to the minus 3 seconds.
Yeah.
More number of atoms will be the excited state.
Yeah.
Slowly they are
Giving time is not
de-excited.
-8 seconds.
No, it can be much faster. It can be 10 to the 15 seconds. You cannot define that it's 10 to the minus 8 seconds. It can be very fast. But my question is not what is the time scale of that upper excited state. That is transient.
10 to the minus 8 seconds. You stay there.
It can be 10 to the minus 15 seconds even. What I'm saying here is that let's say I have 100 molecules, I have up pumped it. Okay, 100 molecules, 100 students have been sent to this floor, from ground floor to the upper state. And then I'm trying to find out how these molecules are coming back to the ground state, because if they are not coming back to the ground state, I will not get energy. And I'm trying to find out how I'm going to get that energy back. What will happen when they come back to this energy, come back to this ground state? That will happen stochastically. What is the stochastic process? Random process. Randomly they will come back. Okay? Suddenly you went back, suddenly he went back, suddenly she went back to the ground state, ground floor. There is no control. And remember, any random process will destroy phase information. There is no phase information, there is no phase correlation. If I can somehow control at what time this group of people will be coming down to ground state, then I can have a phase control. Right? Phase control can be achieved in stimulated emission. What does it mean? I have 100 molecules excited. So in spontaneous emission is incoherent emission. It is random emission. At what time it's emitting, you don't know. But remember, in the beginning we said that all the frequency components needs to be brought in phase. Right? Either you use a hand or some other technique, but you have to bring it in phase. If I cannot bring it in phase, I cannot create laser. So spontaneous emission is giving some light. They are capable of creating laser, but I do not have opportunity to bring them in phase, because that will happen randomly, stochastically. Okay? By taking stimulated emission, what will happen? I have 100 molecule students sitting here in the upper floor. Then I send similar 100 photons again, 100 signal here. Immediately these 100 students jumping to the ground floor. If that happens, then remember all the energy is coming at the same time. They are in phase. Look at this. This is incoming photon, outgoing photon in phase, everything in phase. And that's exactly what I need. I said that, right? If there is randomness, they will destroy each other. Photons are there, frequency components are there. We have the potential to create the laser, but I do not have the technique to bring in phase. It's like harmony, bringing harmony, communal harmony, how to bring them together. So, stimulated emission is the only way you can create a house because it has at least one characteristic, bring them in phase. Okay, but still there is a problem. Problem is that before we go to the problem, we'll clarify one more doubt. When we do this stimulated emission, I have, let's say, two states, two-floor building. First floor, second floor, okay? Sorry, ground floor and the first floor. This is confusing. Huh? First is the second floor. First is the second floor. It's very confusing. In Telugu, right? In Telugu, what do you call it? First floor? Huh? Does it sense second? No, it's first. It's first. Okay. Okay. Okay, anyway, it's a little. What happened? What was that? Let me also enjoy. What is that? Okay. Anyway, so I have, let's say, two floors, okay? Question is, can I make stimulated emission with the help of two floors? There is a basic problem. And what is that basic problem? Boltzmann distribution, have you heard? Boltzmann distribution. What is that distribution? What does it mean by Boltzmann distribution?
Population of ground floor is greater than population.
Yeah. Boltzmann distribution suggests that if you thermally distribute the population, if you try to thermally populate the distribution, no, not population inversion, I'll tell you where. So if you try to thermally populate it, then you will never get higher population in the upper state than lower state. Higher state will have always lower population than ground state. Okay, that's called Boltzmann distribution. Okay, and according to stimulated emission, to achieve stimulated emission, what I need higher population in the upper state than lower state, and that's exactly again reverse. You have to see the world from a spider point of view. Again, entirely opposite world. Okay, and if you do that, then it is called negative temperature. See, Boltzmann distribution is a thermal distribution. Thermal distribution will have always a temperature. Any equilibrium thermal distribution will have a temperature. So any temperature you think of, go to high temperature, any temperature you think of, positive temperature, always you will have lower population here, a higher population here. Always. But if you want to switch it, then